Today we're going to be up to our eyeballs in geometry. I'm going to start us off talking about two-dimensional geometry. I'm going to be giving you a lot of formulas. Candace is going to talk about three-dimensional geometry. She's going to give you a whole lot even more formulas. And finally, Anne is going to do some really cool examples showing you how you can use these formulas to make really good choices in real-life situations. So in my 2D geometry lesson, I'm going to begin by giving you an introduction to the concepts of perimeter and area. And then I'm going to focus on the perimeter issue, and in that issue comes up the word circumference and an issue of units that are called linear units. And then I'm going to finish up by talking about area, and what comes up in discussions about area are what we call square units. So let's begin with an applied example to give an introduction to perimeter and area. Let's suppose that Portland Parks and Recreation is constructing a new ferret run within a small neighborhood park. The enclosure will be 18 feet by 10 feet. How much fencing will be needed to enclose the ferret run, assuming there is a 2-foot wide gate on one side of the pen? How much sod will be needed to cover the interior of the pen? So let's begin by focusing on the fencing question. What I've done here is I've gone ahead and drawn a rectangle and indicated that we have a 2-foot gate on one side of the pen. The length of the long side of this rectangle is 18 feet, and the length of the short side of the rectangle is 10 feet. And the question is, how much fencing is needed? Well, the amount of fencing needed is 2 feet less than the distance around the pen. The distance around the pen is called the perimeter of the pen. So let's go ahead and figure out what the perimeter is. Remember, each long side is 18 feet and each short side is 10 feet. We need to figure out the total distance around the pen. 18 feet plus 10 feet plus 18 feet plus 10 feet. So I think if I add this up and I do it correctly, I end up with 56 feet. But the real question was, how much fencing do we need? So we need to take into account the fact that we don't need fencing for the 2 feet of the perimeter that is being utilized for the fence. So this time, when I calculate the total distance around the pen, rather than adding 18 to 10 to 18 to 10, I'm going to make the observation that there's two sides of length 18 feet, and I'm going to add to that the two sides of length 10 feet, and then I'm going to subtract from that the 2 feet for the fence. So let's see, we had a 56-foot perimeter. We're taking away 2 feet from the perimeter, so we can see that a total of 54 feet of fencing is needed to enclose the ferret run. Looks like one of our ferrets took a header there. Now let's talk about the sod question. Notice that there is no border around the pen now. That's because what we are focusing on now is the interior of the pen. How much sod do we need to cover the interior of the pen? We use the concept of area to measure the interior of a two-dimensional object. A square unit is the basis for area measurement. Here, we will use a 1-foot by 1-foot square as our unit of measurement. I'm choosing to use a 1-foot by 1-foot square because the dimensions of the rectangle have been stated in feet. Here's the question. How many 1-foot by 1-foot squares exactly cover the interior of the pen? Now, if I look at the rectangle I have here of lengths 18 feet and 10 feet, if I scale this back to a 1-foot length, that's a pretty short length in my picture. So I've momentarily blown up a 1-foot by 1-foot square. Now what I'm going to do is I'm going to shrink this little square down to dimensions that match the dimensions, or the scale, I should say, of the rectangle I have on the screen, and I'm going to fit that little 1-foot by 1-foot square into the upper left-hand corner of the rectangle. And the question is, how many of these little squares am I going to need to exactly cover up the entire rectangle? Well, I can see that it's 18 feet across the top of the rectangle. Each one of those little green squares is 1-foot by 1-foot, so I'm going to need 18 1-foot squares in any given row to cover from left to right the rectangle. Similarly, from top to bottom, there's a total of 10 feet. So in any given column, I'm going to need 10 1-foot by 1-foot squares to completely cover the region from the top to the bottom. So altogether, in each row across the rectangle, I need 18 squares, and in each column down the rectangle, I need 10 squares. So in total, I need 18 times 10 squares, which is 180 squares to exactly cover this rectangle. The amount of sod we need to cover the pen is 18 feet times 10 feet. 18 times 10 is 180. Feet times feet, we could say feet, but we don't. What we say is square feet. Look that I wrote it as feet squared, but we commonly state this unit as square feet. You may wonder why. This is one of these issues where the reason why is because that's what we do. So let's focus on perimeter and also talk about circumference and linear units. Let's start with a definition. The perimeter of a closed geometric object is the total distance around the edge of the object. So in our introductory example, that was the amount of fencing needed, the total distance around the pen. Of course, then we ended up throwing out 2 feet, but that was just to make the problem a little more interesting. The perimeter of a circle, the distance around a circle, is typically called the circumference of the circle. Linear units are used to measure lengths and distances. Since perimeter and circumference are both distances, or you might like to think of them as lengths, they are both measured with linear units. Some examples of linear units are feet, miles, inches, meters, centimeters, and kilometers. There's lots of other linear units. I just wanted to throw a few out there that most of you are familiar with so that you get a good idea of what a linear unit is. Let's do a couple of examples. Let's find the perimeter of this star, given that the length of each line segment in the star is 2 centimeters. Well, it seems to me a good place to start is to figure out how many line segments do we have. So altogether, it's looking to me like we have 1, 2, 3, 4, 5 points to our star, and each point on the star has 2 line segments. So in total, there's 10 line segments that make out the distance around the star. So the perimeter of the star is, we have 10 line segments, each of which is 2 centimeters long. So in total, we have 20 centimeters of distance around our star. Let's find the perimeter of this triangle. The perimeter of the triangle is the total distance around the triangle. Well, I can do some simple addition here to figure out the total distance around the triangle. 12 and 13 is 25. Add 5 to that, we end up with 30. The perimeter of this triangle is 30 meters. You know, before I leave this example, I want to make a little note here. The word perimeter is used in casual English just to generally describe the border around an object. So in mathematics, we've simply co-opted that word and added a numerical component to the word. We actually measure the perimeter around the object. Let's do an applied problem. The length of a certain rectangle is 3 more than twice its width. The perimeter of the rectangle is 66 yards. What are the dimensions of the rectangle? Sometimes a picture can really help a person think through a problem like this. Geometry should always kind of bring the idea of picture to your mind. So I've gone ahead and pre-prepared some pictures to help us think through this problem. Here I've drawn sort of a generic rectangle, and I've labeled the lengths of the rectangle as L and W, the lengths of the sides of the rectangle. And I'm thinking here L maybe representing length and W representing width. So we have the length and the width of the rectangle. Now in our little ferret run example, we saw that the perimeter, L plus W plus L plus W, can be simplified to just 2 times L plus 2 times W. So that's going to be the beginning of my formula that I'm kind of developing for this problem. Now we're told in the problem that the length is 3 more than twice the width of this rectangle. Twice the width of the rectangle is 2 times W. 3 more than 2 times W is bringing to my mind that we need to add 3 to 2 times W. So in my picture, I'm going to go ahead and replace L with 2W plus 3. Now the other information that I'm given in the problem is that the perimeter, that's the distance all the way around, 2 times L plus 2 times W, equals 66 yards. So what I'm going to do is I'm going to define W, state the expression for the length, and say that 2 times the length expression plus 2 times W needs to add 66. And you know what? This picture is so descriptive, it's something that I might even want to include in my work when I did this problem for grading purposes. But even if I include the picture, I need to define my variable. So what I'm going to do is I'm going to let W represent the width, which is being measured in yards, of the rectangle. Then the expression 2W plus 3 represents the length of the rectangle. Now, it's looking to me like I'm running out of room to work this problem, so at least for my presentation, I'm going to get that picture out of the way. Now, we know a formula for the perimeter of a rectangle is 2 times the length, which is represented by the expression 2W plus 3, plus 2 times the width. The width is just represented by the letter W, and this needs to equal 66 because the perimeter of the rectangle was 66 yards. Now I want to speed through solving this equation. I have 4W plus 6 plus 2W equals 66. So 6W plus 6 equals 66. That's a whole lot of 6's. Subtracting 6 from both sides, we have even more 6's. But then when we simplify, phew, we're finally rid of some of them 6's. 6W equals 60. And so if I divide both sides by 6, because I think we should just kind of end on a 6 kind of note here, we end up with W equals 10. So it seems like the width of our rectangle is 10 yards. If the width of the rectangle is 10 yards, since the length is represented by 2 times the width plus 3, 2 times 10 is 20, and 20 plus 3 is 23. So I think the solution here is that the width is 10 yards and the length is 23 yards. But I do want to check my numbers and make sure that they add up. So let's do a little check here. If we take 2 times 10 yards, and we add to that 2 times 23 yards, let's see, that's going to be 20 yards plus 46 yards, which is 66 yards. So this answer checks, so I can go ahead and state my solution, that the dimensions of the rectangle are 10 yards by 23 yards. I also could have said the width of the rectangle is 10 yards and the length of the rectangle is 23 yards. There's lots of correct ways to write my conclusion. I just need to make sure that it completely conveys with units the answer that I found to the problem. Let's get some formulas out there for perimeter and circumference. We just used this formula in our last example. If L and W are respectively the length and width of a rectangle, then the perimeter of the rectangle P is given by the formula P equals 2L plus 2W. We can take that formula and extend it to the special rectangle called a square. If E is the length of each edge of a square, then the perimeter of the square P is given by the formula P equals 4E. We can see in our picture, E plus E plus E plus E is 4E. Here we have a couple formulas for the circumference of a circle. If D is the diameter of a circle and R is the radius of the same circle, then the circumference of the circle C is given by the formula C equals pi D, which in turn equals 2 pi R. We can see in the picture that 2 R's make a D, so this is just really two ways of saying the same thing. If we know the diameter, the circumference is just pi times D. If we know the radius, the circumference is just 2 pi times R. Let's use the circumference formula. Let's find to the nearest tenth of a centimeter the radius of a tabletop whose circumference is 550 centimeters. So let's go ahead and let R represent the radius measured in centimeters of the tabletop. One of our formulas for circumference was 2 pi r. So it must be the case that 2 pi r equals 550. I can isolate r by dividing 2 pi from both sides of the equation. And when I do that, I end up with the equation that r equals 550 over 2 pi. Now the problem explicitly asked us to find to the nearest tenth the radius of the tabletop. So we need a decimal representation of this number. We need to, on our calculator, divide 550 by 2 times pi. Now I need to remind you about something when you're performing this type of division. It's really easy to not really think too hard about what we're putting into our calculator and to type 550 divided by 2 times, if we're going to use a decimal approximation for pi, 3.14. But remember order of operation. Division and multiplication have the same priority in order of operation. So if this is what we type into our calculator, the calculator is going to find 550 divided by 2, which is 225, and then it's going to multiply that number by our decimal approximation of pi. But we don't want pi being multiplied by 225. We only want pi to be multiplied by 2. So in our calculator, we need to make sure that we put the 2 times our decimal representation of pi in parentheses. So let's look at our calculator. Now, when I gave my description about how I'm going to plug this into my calculator, I used the decimal number 3.14 rather than the symbol pi. That's because on the calculator that I'm working with, there is not a pi key. Lots and lots of calculators have a pi key, and if you have a pi key, go ahead and use it. Since I don't have a pi key, I'm going to use this decimal approximation of pi, 3.14. So I'm going to take my 550, and I'm going to divide by, in parentheses, 2 times 3.14, close the parenthesis, and hit equals, and I get about 87.58. But the problem told me to round to the nearest tenth, so I'm going to round this to 87.6. So R is about 87.6. Since this is an applied problem, I need to make sure that I write a complete sentence answer. The radius of the tabletop is about 87.6 centimeters. Let's talk about area formulas and square units. Let's begin with our rectangular area formula. Let's go back to our ferret example. The amount of sod that we ended up needing to cover the bottom of that rectangle was 18 feet times 10 feet. That was the length of the rectangle times the width of the rectangle, and that indeed is our rectangle area formula. If L and W are respectively the length and width of a rectangle, then the area of the rectangle A is given by the formula A equals L times W. Squares are special types of rectangles. They're rectangles where the length and width are equal to each other. If E is the length of each edge of a square, then the area of the square A is given by the formula A equals E times E, which we read as E squared. Let's ponder that. Square. Squared. I bet there's a connection there. Let's talk about area units. 1 linear unit by 1 linear unit squares are the unit of measure for area. Consequently, area is measured in squared linear units. In our Farad example, we had a 1 foot by 1 foot square, and the unit that we used for measuring area was feet squared, or square feet. Some examples of area units are square feet, square miles, square centimeters, square kilometers. There's some other peculiar kind of area units out there like hectares and acres, but you probably want to stay away from those unless you have a calculator with a unit conversion key or a table or a really good memory. Let's do an applied problem. Let's find the length of each side of a square whose area is 25 square kilometers. So if we let x represent the length of each side of the square, and we're measuring this length in kilometers, then we know that when we square x, we need to get 25. We've not really talked about how you solve an equation like this, but I think we can figure it out. What number do you multiply by itself and get 25? Well, you might be thinking, you know what, there's two numbers I could multiply by itself and get 25. Positive 5 times 5 is 25, and negative 5 times negative 5 is also 25. But lengths can't be negative, so we can discard the negative 5 answer, and we can just go ahead and jump to our conclusion. Each side of the square is 5 kilometers. And let me just remind you, if we take 5 kilometers and multiply by 5 kilometers, the numerical part is 25. The unit part is kilometer, but that's a real tongue twister. Luckily, we don't say it that way. Luckily, what we say is square kilometers. Now I'm going to move to another geometric object, but I'm going to begin by asking this question. What is the area of half of a rectangle with sides of length b and h? You know, I said earlier I used L and W for length and width. I don't need to use L and W for the lengths of the sides of a rectangle. Here I have a rectangle, and I'm designating the lengths as b and h. The area A of half the rectangle is 1/2 b times h, because the area of the entire rectangle is b times h. Let's take that rectangle and cut it in half. But I'm going to cut it in half in a way that you might not anticipate. I'm going to cut it in half along the diagonal. And I'm going to go ahead and shade the region below that diagonal, and I'm going to make the observation that the object underneath that diagonal enclosed in the rectangle is just a right triangle. So when I get rid of the rectangle, I have an area formula for a right triangle. The area of a right triangle is 1/2 b times h. In this context, b is representing what we call the base, and h is representing what we call the height. I'm going to talk about that a little bit more a little later on. Same problem. Let's cut the rectangle in half, but this time I'm going to do it in an even more bizarre sort of way. I'm just going to pick an arbitrary line, and you're thinking, hey, that line doesn't cut the rectangle in half, and I'm saying, hey, you're right, it doesn't. But what it does do is it creates two rectangles out of one. So let's focus on the left rectangle, and let's cut the left rectangle in half with a diagonal. Let's cut it in half with that diagonal there, and let's shade below that diagonal. Now let's focus on the right rectangle, And let's cut that rectangle in half with this diagonal, and let's shade below that diagonal. Since I've cut both the left rectangle in half and the right rectangle in half, I also have cut the whole great big rectangle in half. So the area of the region that I've shaded here is 1/2 b times h. Let's give the rectangle the kibosh. And once again, we see that the area of this triangle is 1/2 b times h. Notice that b is the length of one of the sides of the triangle, and then h is the distance from the vertex opposite the side that we've designated as the base. It's the shortest distance. That's what this right angle is up right there. So let's answer this question. What is the area of a triangle with a base of 5 meters and a corresponding height of 3 meters? This is an easy question to answer. The area is 1/2 the base, which is 5 meters, times the height, which is 3 meters. So altogether, we have 7.5 meters, which we usually call square meters. So this was an easy calculation to make. Let's explore the geometry behind this calculation. I'm going to begin by drawing a 3 meter by 5 meter rectangle. And what I'm going to do is I'm going to cut this rectangle in half with triangles of various shapes. First, I'm going to use a right triangle. Notice that this right triangle has an area half the area of the rectangle. Then I'm going to use an isosceles triangle. Again, this triangle has an area half of the area of the rectangle. Then I'm going to use another triangle, and this triangle has an area that's half the area of the rectangle. It turns out that our triangle can actually extend outside the rectangle, like this. In this picture here, this length is what we would call the base. So the vertex that's opposite this base, I just need to hunt. This is the only point that's opposite the base. So when I try and draw a perpendicular to the base, I can't do it. So I have to extend a line through the base, and then I can draw a perpendicular from the vertex to that line. And notice that that distance there is the 3 meters. It is h. And so the area of this triangle is indeed 1/2 of 3 meters times 5 meters. So the area of each one of these triangles is 7.5 square meters. Now in all 4 of these pictures, the side that I'm using as my base is the bottom side of the triangle. I don't have to do that. I can use any of the 3 sides of the triangle as my base. And to maybe help you see what I'm saying, I'm going to mix this picture up a little bit for you. Notice that all I did with these triangles was I spun them around. So they're the exact same triangles, they've just changed their orientation. So the area of all of these triangles is still 7.5 square meters. But now none of the bases are the bottom side of the triangle. As a matter of fact, none of these triangles really have a bottom side. I just need to make sure that whichever side I call my base, I use as the height the distance from the vertex opposite that base to the base, or at least to the line passing through the base. Now I'm going to talk about a shape called a trapezoid. A trapezoid is a 4-sided object that has the property that 2 of the sides are parallel to one another. So in this picture, the top and bottom sides are what we call bases. They are the sides that are parallel to one another. So I'm going to assign some letter names to some certain lengths in this picture. I'm going to call the lengths of the bases b sub 1 and b sub 2. And then I'm going to call the perpendicular distance between those 2 bases, the shortest distance between those 2 bases, h. And I'm going to use these 3 letters to come up with a formula for the area of the trapezoid. Now, in order for me to come up with this formula, I'm going to rearrange the pieces of this trapezoid a little bit. I'm going to begin by metaphorically getting out a pair of scissors and cutting out the rectangle in the middle of the trapezoid. When I do this, I'm left with triangles to the left and right of that rectangle. I'm going to push those two triangles together, and I'm going to push the rectangle off to the side. And when I do this rearrangement, I'm left with a triangle whose height is h, and I'm left with a rectangle whose height is h, and this funny looking object has exactly the same area as the trapezoid that I started with. Now in this picture, I can see that the area of the rectangle is going to be b1 times h. I can't quite see what the area of the triangle is though, because I don't have an expression for the base of the triangle. But if this entire length is b2, and this piece of that length is b1, then this piece of the length must be the entire length, b2, minus this length, which is b1. So now I can see what the area formula is for the triangle. It's 1/2 of b2 minus b1, that's the base, times h. So let's get the b2 line out of there for the time being, and let's go ahead and come up with a expression representing the areas of these two objects. So the area is going to be the area of the triangle, which is 1/2 of b2 minus b1 times h, plus the area of the rectangle, which is b1 times h. Let's simplify. I need to distribute both 1/2 and h through the first set of parentheses, actually the only set of parentheses, and when I do that, I'm left with 1/2 of b2 times h minus 1/2 of b1 times h, and then I need to add the rectangular area, which was plus b1 times h. I have some like terms to combine. There's two terms that have the variable factors b1 and h. If I take a whole b1h and I subtract half of b1h, I'm left with half of a b1h. If I have a pie and somebody takes away half of it, I still have half of it. I also have half of b2h. Now, both of these terms have factors of 1/2 and h, so I can kind of undistribute those factors. Undistributing isn't really called undistributing, it's called factoring. So I'm going to factor out a 1/2, I'm going to factor out an h, and when I do that, I'm going to need a term of b1, that will give me 1/2 b1 times h, plus a term of b2. That will give me 1/2 of b2 times h. And this is my formula for my trapezoid, because remember, this triangle and square could be pieced back together into my trapezoid. So here's our trapezoid area formula. The trapezoid area A is given by the formula A equals 1/2 times the height times the sum of the two bases. Let's do an applied trapezoid problem. Let's find the perimeter and area of the given trapezoid. Well, let's answer the perimeter question first. The perimeter question is asking us what is the distance around this trapezoid. So that 12 meters length is completely irrelevant to the perimeter question. So let's kind of put it in the background for the time being, and let's just say that the perimeter of the trapezoid is, I don't need to write down any work. I can add these numbers up in my head, and maybe I can even do it correctly. 8 and 20 is 28, and if I add 29 to that, that's going to be 57, and if I add 13 to that, that's going to be 70. So the perimeter of the trapezoid is 70, but if I wrote that down as my answer, I might be dinged a point or two, because there's units in this problem. The perimeter of the trapezoid is 70 meters. So now let's answer the area question. In order to find the area of a trapezoid, I need to first identify what are the two bases. The two bases are the sides that are parallel to one another. And it's the 8-meter side and the 29-meter side with this orientation of our trapezoid that are parallel to one another. So the 20-meter side and the 30-meter side are irrelevant in terms of the area question. So they're going to go to the background. But notice that the 12-meter length, came to the foreground. That's the height between these two bases. So the area of the trapezoid is, this time I do think I need to show a calculation. It's 1/2 times the height, which is 12 meters, times the sum of the two bases, which would be 8 meters plus 29 meters. So let's see, 2 goes into 12 6 times. 8 and 29 is 37, so 37 times 6, can I do that? Well, 30 times 6 is 180, and 7 times 6 is 42, so I do believe that we're left with 222. Boy, I guess repeating digits are the theme today. Remember all those 6's? Now we got a bunch of 2's, and we need to make sure that we include our unit. And even though I like to say meter, meter, what we really say is square meter, and we write it as meter squared. One more formula. If r is the radius of a circle, then the area of the circle A is given by the formula A equals pi r squared. The ancient Greek mathematicians got obsessed with this issue, and somebody finally figured out the answer to the question. The area is pi r squared. So let's do one last example. Let's find the diameter and area of a circle whose circumference is 12 pi yards. Well, you know, the diameter of a circle is twice its radius. The area of its circle is pi times the radius squared. So I think a good starting point here would be to figure out what is the radius of the circle. So let's let r represent the radius of the circle measured in yards. Our area formula for a circle is, we don't know the area, we know the circumference. The circumference formula for a circle is 2 times pi times r, and that equals 12 times pi. To isolate r, all I need to do is divide both sides of this equation by 2 pi, and I can see that my original equation is equivalent to the equation r equals 6. So the radius of this circle is 6 yards. So let's just go ahead and state our conclusion to the problem. The diameter of the circle is 12 yards because the diameter is twice the radius, and the area of the circle is pi times 6 yards squared. 6 squared is 36, so the numerical part of the area is 36 pi. And let's see, when we multiply our units, we're going to have yards, which we really call square yards, and we write as yards squared. And with that, I'm done with two-dimensional geometry, and Candace is going to take over with three-dimensional geometry.